Is it this camera? It is this camera. So what I'm talking about with that, if we're going to try that next time, is if this was chapter 15, again, we're doing 11 and 12 today, but I just want to show you what it would look like, okay? Is that if I hosted 15 live, and I'll wait for like 1 or 2 of you to sign in. I'm not going to wait for everybody to sign in for this one. So maybe a couple of you sign in on chapter 15, just so I can show you what it would look like, okay? Let's see if you guys think that this would be helpful. I actually think, yeah, this is fine. Go ahead and sign in. Just a couple of you, maybe, if you have your phone out. And that way I can at least start it and you can see what it might be like. Yep, Tony, that's enough. So what it would look like is, that's really the countdown thing too. I meant to click lecture and not the game. But anyways, this is what it looked like. There's a slide, there's a slide, there's a slide, blah, blah, blah. I'll talk about the slide. And then there's a little question, where on this chart would nostril hairs fall? And then you guys would be able to put a little pin down in your game. And then I would be able to say, okay, let you guys put your pins down. We do that. And then it would show where you put your pins. And I'd be like, okay, it would actually follow in this area. And that's because blah, 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 blah. More lecture slides, more lecture slides. And there might be other questions in between. So this is me actually lecturing, but interspersed with questions. Does that make sense? Okay, because this is where I feel like people don't actually watch the lectures until like a day or 2 before the exam. You're still welcome to go back and watch the recorded lectures, but this way you're getting more exposure to that content that I'm hoping will help a little bit more with your time management. Make sense? So it's going back to kind of old school, but still incorporating some interaction. And how many of you guys just play the lectures like in the background while you're doing something else instead of actually engaging with the lecture? So this is hoping that will get you to engage with the lecture. And I won't be calling on you guys that day either. I'm just assuming if you completed the Kahoot questions, you engaged and you'll get your points for participating that day. So that takes away that as well. We fans of that? Does that sound okay? Okay, so we'll try that for 15 and 16 and we'll see how that goes. But for today, I'm sorry, we're doing the old school thing. It'll be in class, in person, yes, instead of what we usually do in class. Good job for you guys that signed in. I know that's ridiculous, but okay. So we're going to do the regular thing today where I am going to call on you guys, okay? All like 7 of you that are in the class today. We still have, if you guys haven't heard about CLO, had COVID and she's been out with COVID and that's why she hasn't been here and she still hasn't taken her unit 2 exam. She's literally got COVID. So we're waiting on her. So we won't be like reviewing the whole unit 2 exam because I still have to wait for her to take the exam. Well, I will touch on a couple of the questions just for perception wise to help you guys understand. Maybe there's some stuff that we can think about when we're taking our next exams, put that into perspective. We'll do that. Okay, for realsies. Get this set up. I figured this out. This was a thing on here that I've been missing. So this is chapter 11. All right. So we're gonna do chapter 11 and then chapter 12 today. Chapter 11 covers microbial control methods, things like autoclaving, washing your hands, using disinfectant, cleaning wounds with alcohol or hydrogen peroxide, and whatever. So that's gonna be chapter 11. Chapter 12 has to deal with antimicrobial drugs. So actual drug treatment of microbial infections. So we'll be going over that. One question that I get a lot with chapter 12 is, I feel like this is loud compared to me talking volume. I want it to be there because I like it, but it was loud. One thing to get a lot of questions about with chapter 12, they're like, man, that's a lot of drugs. Do I have to know all of them? Yes, And wait till you get to pharmacology in nursing school. It's way more drugs than this. So it's one chapter with a lot of drugs in it. And yes, I do expect you to know the drugs and generally how they work. A lot of the exam questions for chapter 12 will be questions like, which of the following drugs affect the cell wall of bacteria? Which of the following drugs affect fungal infections? Which of the following, and that sort of stuff. And there'll be a whole list of drugs, and you have to know which one it is in that list. So there's a lot of them. I feel like chapters 11 and 12 are flashcard chapters, generally speaking, okay? So if you feel like that's a flashcard chapter for you, you're probably right. And so use your judgment on that and where you feel like that would be appropriate for your study, right? Chapters 15 and 16 are not, and that's why I'm trying to push more for having a little bit more lecture time with 15 and 16. And if it works well and you guys like it, we'll do it for 17 and 18 also, and probably moving forward well, 17 and 18. When we get to 19 and 20 and 21, we're in the presentation days, okay? Now you guys are unique because I only had, I think, 11 of you left. So Azalee did end up dropping the class for personal reasons. Okay? So, and Sonia has dropped the class too. So I think we're down to 11 now in the class. And obviously not all of us are here. So 1, 2, 3, and we've got CLO. I think what? Yes, right. So I feel like that's okay. Where is the thing I had open?
The last exam went well for your courses.
So you guys did the best yet again. Who's surprised? So I feel like that's not that unusual from what I'm expecting anymore. This is really hard for me to see this. What is this? Sorry, I'm trying to find something on here and I can't do multiple things at the same time. Sorry. Okay, so yes, so you guys did better than, and you did approximately on par with my summer class, approximately, just a couple points lower, but that's actually pretty impressive to me. And if you guys are saying, so yeah, I know some of you guys are probably sitting there like, huh, it's not the score that I wanted. And I believe you, but most of the class, not all of the class, but most of the class did a little bit better on this test probably than you did comparatively to unit 1. Or not everybody, like I said. But this is one of those moments where I say some self-reflection might be needed. So take that moment to, number 1, did you do everything that you could to study appropriately for that? Be honest with yourself. You're not having to tell me. You're only having to have that discussion with yourself, right? So be honest with yourself about it. Did you do the things that I suggested? Did you talk with people and explain out the concepts? Did you, have, group time to discuss the concepts? Did you discuss it with your steering wheel? And I will say that nobody came to my office hours to discuss the concepts with me, but are you doing other things to discuss it with other people? So FYI. So this is a time to reflect on that. So another student came to me and she has, there's not anybody in this class, but she has a 77 in the class. And so she's like, what is the reality of me being able to get a B in this class? So I'll point something out. I know we still have quizzes and little things like that. Those things are already computed into your grade. There are 50% of your grade hasn't been commuted into your grade at all yet. 50%. That is your disease presentation, 10%. That is your unknown report, 10%. That is unit 3 exam, 8%. That is the lab final, 10%. And that is the lecture final, 12% of your grade. So that's all 50% altogether right there. That's a lot. So is there opportunity to raise your grade? Oh, absolutely. Is there opportunity to tank your grade? Oh, absolutely. Everybody. So that's the thing that I want to remind people too. It's like some people sitting there with Bs, the likelihood of people's grades changing a lot at this point, what I find is if you continue to do what you've been doing, the likelihood of your grade changing is not very good. Just being honest, okay? I might see a little bit of rise in grade because of the boost that we get from the presentation and the unknown report. They're meant to be boosters, okay? So you might see a little bit of a boost if you do well on those assignments, but people usually do poorly on the exams if they continue to do what they've been doing on the exams. So what I say is if you've been getting A's or B's on your exams, you'll probably get A's or B's on your exams. If you've been getting C's or D's on your exams, you're probably going to continue to get C's or D's on the exams, unless you do something different to help with the studying. Okay, so that's the reality of it. That's just honest transparency there. If you want help with that, you're always welcome to reach out to me or the SSOC. If you are somebody that has not made a passing grade on an exam yet, then you will have gotten an email from the SSOC reaching out to you. If you didn't get that email from the SSOC, then you've made at least a 70% or higher on at least one of your exams. But if you haven't made a 70% higher on at least one of your exams, you've got an email from the SSOC reaching out to you with their resources. Make use of it if you feel like it's useful to you. That's why I had them email you. So keep that in mind. That's a good resource as well. We will touch on a couple of questions on Unit 2 when we get into the lab, because we'll have time in lab today. It's going to be a shorter lab today. So we will do that when we get to the lab. We will also go over the whole lab exam because we only have 2 lab exams, and the second one is partially comprehensive. So some of the stuff we will see again. It might not be the same questions, but it'll be questions about the same content. And so I want to actually go over that exam with you guys, okay? So we'll do all of the lab midterm during the lab. We're going to go over the whole thing. And we'll talk about some of the questions on Unit 2, just because it's like a perception thing about the questions, and I want to clear that up. Yes. Yes, yes. So I'll let you guys look at it if you want to. Today's lab is going to be a little bit more engaged, so there won't be like time during the lab to really come look at it, but after the lab, or it doesn't have to be today, it could be, on Thursday or something like that. So whenever you get a chance, you guys are welcome to look at your exams that way. Okay. What else? I got the announcement today about the Thanksgiving thing. So this is another thing with this class. This class is on a Tuesday evening. That's a suck thing for Thanksgiving week for all of us, okay? So we have the opportunity, since there are only 11 of us, our class period during presentation time, the time that we have for the presentations, I usually limit to 8 people a day. So we can fit 11 people across 2 days, easy, okay? So if you want to, I can free up our Tuesday night presentation day. Now, the other problem is Tuesday night isn't just the presentation day, it's also the lab exam day. So here is my offer to only this class. And Maria, this doesn't get out, okay? Because I know Maria wanted to, this doesn't go out to your class. But only for this Tuesday night class, okay? If you want to join a different class, like Tuesday morning's class or a Monday class for the lab exam, you contact me and let me know as soon as possible, okay? Tuesday night sucks. But if you want to take the Tuesday night exam, I'll be here for you. It's fine, okay? But if everybody contacts me saying, hey, I'd rather take it on Tuesday morning, or I'd rather take it with your Monday class, then we won't have it on Tuesday night. But I'm gonna leave it up to you guys. You guys have to reach out to me about that, okay? So just shoot me an email saying, can I take it on Monday? So the times I have available are either Monday at 11 a.m., Monday at 1 p.m., or Tuesday at 11 a.m. So those are my times that would be available for Thanksgiving week for your lab final, if you don't want to take it at 6:45 p.m. on Tuesday of Thanksgiving week, okay? Make sense? So you'll still have to take it one of those days that week. I can't get you out of it completely, but maybe not at 6:45 p.m. on Tuesday if you don't want to. Okay? You guys are the only class I'm offering that to. So think about it, and if that applies to you, you'd like to take it on a different day at a different time, and please email me as soon as possible, because I do have limited spots. Okay, so I'm gonna have like 2 spots on Tuesday morning, so I can't fit everybody all on one day at one time, unfortunately. But I can pepper you throughout. Okay, and also if you're like, hey, those times don't work for me, but can I come in on Tuesday at 1, which is also, I'll offer that too. Tuesday at 1 is also open. It's during my office hours, but I'd rather do that than my office hours. So if you're available at Tuesday at 1, I will also accommodate you then, okay? Monday or Tuesday at either 11 or 1. Make sense? So email me if you have a preference on that. It's open to you. Okay. No offense, if you can make one of those times, I would prefer that you try to, so that we don't have to have class at all for you guys at night on Tuesday? Because that's what we're talking about here, is potentially not having to come in that night. Seven to four, okay. So yeah, if you guys already work and you can't get off of work, because again, this is Thanksgiving week, right? And so that might be hard for some people because other people already have taken off on Thanksgiving week. But if you can't get off for one of those times on Monday or Tuesday of Thanksgiving week, you email me about that, okay? Just email me about that. Can't make it those days, can we do it on some other time? If that's the case, I also don't mind staying later on Monday so that I can get off from Tuesday. You get what I'm saying here? Yes, yes.
So if, let's say all of us didn't take we are took the last final at a different time, we would just do our presentations when we did.
Yeah, you would do, so we're not even gonna do, so if we have that and we can all agree to take the lab final on a different day, I'm gonna be pushing all of the presentations to either the previous Tuesday or the Tuesday following that. No presentations on that day at all. So literally no class for us on our normal time on that Tuesday before Thanksgiving. Right, so like I said, this is only an option for you guys. You think to yourselves, what's gonna work for you? And if we've got some people, like we might have Duncan and we might have Cassie, that might not be able to make it on those morning times on Monday and Tuesday, then again, if I have to have a section that is available at like 5 p.m. on Monday, would that work for you guys? Okay, that'll be better for you too? Okay.
Yeah.
'Cause I don't mind staying, because it's not gonna take me, it's not gonna take you guys 2 hours to take the test. We already kind of know that, right? It's maybe gonna take you an hour tops. So I'll offer a section that's just for you guys to come in at 5 p.m. on that Monday too. So you let me know what time you want to come. Okay. So we'll say Monday and Tuesday. You have Monday and Tuesday at 9, sorry, excuse me, at 11 or 1, or you have Monday at 5 p.m. You email me with your preference. Absolutely. Absolutely. Yes. So once I hear from all of you and okay, yeah, so we'll talk. Yeah. All right. Sorry, guys who are online. All right. We ready to get started? All right. Kaylee, I don't know if you heard me talking about that stuff. Did you hear me say any of that stuff that I just said, Kaylee? I mean, you're joining us online. I'm assuming you're coming to lab anyways. Okay, good. Okay, yes. So you email me with your preference too if you have one. And if you are confused about any of it, just see me during lab and we'll talk about it. Okay, we good? Yeah, because a Tuesday night, yeah, the Tuesday night before Thanksgiving, I mean, that's kind of rough. Asking people to come in on Tuesday morning is one thing, but Tuesday night, you know.
Well, and we can push the presentations and only 11 of us. We don't even have them come in.
Yes, yes, yeah, that would free you up completely on that day, okay? Yeah, so for me, from my class, that would actually free you up that whole week. Well, I guess if you're coming in on Monday, just depends on what day you choose to come in and visit it. But yeah, no Tuesday or Thursday on that week, right? So that's what I'm trying to say. Okay, let's do the thing here. Just to be clear, so I talked about this in one of my other classes, and I'm going to mention it to you guys too. I'm on Faculty Senate. In fact, I'm a senior elected member on Faculty Senate, which is Faculty Senate is like the group of the faculty that make like the policies and procedures and rules and changes for the university stuff. Okay, so I'm a senior member on there, and I've been elected to represent the School of STEM. So it's my second year serving. You serve 2-year terms, and it's your second year, you are senior member. I am also chair of the academic, academic policies and student affairs subcommittee within Faculty Senate. And so I'm the actual chair of that committee as well. So they're the ones that deal with like procedures and things like that that affect the students in academic affairs. Last year, we proposed that we have the whole week off for Thanksgiving. And we had a vote amongst faculty that as long as it kept the days off for the staff, because staff actually get paid days off during fall break, okay? So as long as it kept the paid days off for the staff, that faculty approved moving Thanksgiving week off, but losing fall break. It was a trade-off. We couldn't keep both of them, okay? But this was supposed to be beneficial for people that have kids, because kids get all of Thanksgiving break off in every single district in Oklahoma, okay? And faculty approved that. The staff did not approve it. There's reasons for that, okay? And so it fell to the students. You guys might remember you got an email last year that had a whole big long list of survey questions on it. It was an optional survey that went out to a lot of people. All right, most students didn't complete the survey. Okay, if you did, I want to give you a high five and a congratulations, but you probably didn't. We have thousands of students and we got 70 responses.
Wow. I don't remember giving it,
Right.
but.
Yes. And so the other aspect of this is it wasn't well advertised what the survey's purpose was or anything like that. 70 students answered back, and based on those 70 students' responses, there was no definitive decision on whether or not students wanted to change fall break or Thanksgiving break. And so the administration decided to keep things the way they were. So now we have to have butts in seats on Mondays and Tuesdays of Thanksgiving week. We have had it this way for years. It's always been fall break and then part of Thanksgiving off. But Stillwater has the whole week of Thanksgiving. They don't have a fall break. And every other school district in Oklahoma has the entire. And I tried. That was my motion that I put in place, and I tried. But the way that it was sold was not sold appropriately because people that were selling it have more power than I did. Okay, that's politics, right? That's politics. That's politics, politicking, and it's just the way that it is. Okay. Am I a little bitter about it? Okay. Will I say though that I was thankful for fall break? I mean, absolutely. So there's pros and cons to both sides of it, and I'm completely respectful of that, but that's the reality of this situation, okay? So I also don't have tenure. So I can't just give you the week off because I want to. So other professors can kind of wiggle that room, and they're not going to get in trouble because they're tenured. I'm not tenured. There's a risk for this university losing tenure as well. It's the only two-year university in the whole state that offers tenure. And so we're trying to defend it. And it's a fight. I'll just put it that way. Okay, it's a fight. The process that we've used to determine about tenure is weak at best. And so we're trying to improve that, and that's something that I'm improving on because I'm sure you can imagine, my background is stellar, but I'm not. That's not everybody. So I'm trying to save it for people like me and Dr. Tim and folks like us that haven't gotten tenure, that we work our butts off and deserve it, compared to people that are the ones that are ruining it for the rest of us. The reason that I came to this school was because it offers tenure for people with master's degrees like me. So if they were to get rid of tenure before I got tenure, I would not be staying here because it doesn't pay enough. That's my goal, is to get tenure, and then I can give you more extra credit. I can give you Thanksgiving off and stuff like that, and have more leeway with stuff like that. So bear with me. You guys get to suffer until I get to that point, okay? So you won't hear a lot about this stuff, but is anybody in here in SGA by any chance, student government? Okay, because I would also say that I'm trying to get more students to participate in decisions like this as well, because we have had no representation from any students whatsoever in any of this policy making, just because there hasn't been communication about when the meetings are and where they are and stuff like that. So I'm also, because I'm the chair of that committee, I'm trying to get a tuition waiver for our SGA representatives that actually go to the committee meetings.
My best friend was finally called from Stillwater's
Mhm.
SGA campus, and they get a lot.
Yeah.
Involved in that, like scholarships.
Yes. Yeah, so I'm trying to get more of that here for this campus, and I'm working with that. We have money set aside for that. It's just not being used for it. And so anyways, I'm doing a lot more. Like, you guys see me do a lot for this class, but I'm telling you, I do a lot more in the background too, to try to make the experience for students better and better and better, and getting students involved, because I cannot tell you how many policies and procedures are instilled without consulting a single student. It is wild. So I'm trying to change that. So be here for me if I ask you, I ask you to, like, hey, there's a survey coming out. Those are your opportunities to get involved with that stuff. Okay. All right. Let's do the thing for real. Yeah. Yeah, right now, if I were doing something that actually affected you right now, I would tell you guys. But like right now, literally the only thing that's on my plate is trying to get that scholarship in place for SGA to participate. And I'm communicating with SGA about my meetings coming up. Hey, maybe you guys could come to this just to be involved and whatever. But that's all I can do right now. So we will soon, they are changing the campus-wide learning objectives, which are the things that say, like, our graduates will have, knowledge of the global impact of their actions, those weird learning objectives that apply to the whole university. And they haven't really been changed for decades. And so we are in the process of changing those. They've gone through a certain committee that designs them. and the administration didn't like those ones, and so they're gonna get kicked to my committee. And so if I need your opinions, I will be reaching out to you. I don't know about that yet, though. So that might not even be all your my students. So that's, I don't know if you guys know this, but also academia moves very slowly. Wildly slowly. So whatever. Just keep that in mind. All right, so double check you are signed in. We're gonna get going for realsies. Got my names pulled up. And we're gonna get going with our first questions, an easy one, I think. Chapter 11. All right, we got Cassie first. All right, our first question for Kahoot. What is decontamination? My question for Cassie is going to be, what is disinfection? Actually, what's sterilization? I'll make it easier for you. What is sterilization? I'll make, yes. And don't worry, if you didn't hear her say her answer, I'll cover it again. She did say it correctly, though. All right, so decontamination is the mechanical removal of microbes. What we can think of it is like separating the microbes from the object. This could be literally filtering liquid, for example. Are we necessarily killing the microbes if we filter it? No, we're removing them though. So that's an obvious example of that decontamination process. Another one would be like washing your hands. Now, when you wash your hands, you might be using suds that disrupt the membrane. We'll talk about an example of that towards the end of our Kahoot here, which will be about surfactants and detergents, okay? So those can disrupt the membrane, but they can also help physically remove the microbe from how it's stuck to your skin. And so that's also going to be decontamination. Sterilization, like Cassie told us, sterilization is the complete like destruction of all microbial life. So if we are destroying all microbial life, that is sterilization. Disinfection is going to be destroying most microbial life from usually inanimate surfaces. Okay, so if we are destroying, not mechanically removing, but destroying those microbes, disinfection. And again, most microbial life. What types of organisms, Jillian, what types of organisms might survive? What are the ones most likely to survive? There it is, endospores. That's exactly what we're looking at. Endospores, because they are so hardy and so resistant, when I say we're disinfecting and not everything gets killed, when you look at Lysol and it says 99.9% of microbes are killed. That 0.1% is the endospores almost every single time. They're very hardy and very resistant, okay? So that's what disinfection is talking about there. Sterilization, we're actually killing the endospores too. Okay? Hardier than endospores are going to be prions. Now they're not alive, so they're just misfolded proteins, but they're so resistant that even autoclaving won't get rid of prions. It's not hot enough for them to basically like be denatured. So we have to actually autoclave them at 135 degrees Celsius instead of 121 like traditional autoclaving. So this is a weird thing. It's very, very rare to see a prion. So typically if somebody is having at a young age some sort of dementia that doesn't fit their family history or anything dealing with their health prior to that, and we suspect it might be a prion disease, or we're going to be drawing CSF or something like that, and it's going to come through the lab, we call up to the lab and we tell them, we might have prions. And then the lab has a procedure that they put in place. Everything's being done on those diapers, you know what I'm talking about, those little diaper pads that they have. They're disposable. Well, they will literally double glove and things like that. And so that like we are disposing of every layer as we're switching gloves, we have a glove underneath it and stuff like that, so that everything can be disposed of and incinerated as opposed to potentially being autoclaved and reused again, because proper autoclaving won't get rid of the prions and we can't risk that. If somebody has a prion infection and they go to the dentist and the dental instruments are dealing with the nerve, like a root canal or something like that, and then that dental instrument gets autoclaved, and then we use that dental instrument on another person later. It's sterile, there's no microbes, but there might be prions on it. And you can actually transmit prion infections that way. Now, like I said, prion infections are incredibly rare, so we are not worrying about them on a day-to-day basis because it just doesn't make sense for us to. So I'm not trying to induce panic here, okay? Which there certainly was panic involved in mad cow disease during that era, if you were alive for that, and many of you weren't. Okay, but I'm telling you, in the 90s, when mad cow was first discovered as this thing that was actually happening, and they were killing all of the cattle in Europe. I mean, all of them. They had mass cullings of all cattle in Europe because of this mad cow situation. And even today, if you have been to Europe between 1990 and like 1999, you cannot donate blood ever for the rest of your life because of mad cow disease. So it's that serious. And there's still people that might be popping up from visiting Europe during the 90s that could potentially still just suddenly have, you know, that prion and start multiplying in their brain and leading to spongiform encephalopathy. So is it scary? Yes. Is it likely? It's not. Yes.
Weird, but like, do we know that it's more common in animals because it just spreads quicker in animals than it would in humans?
Right. So the problem, yeah, the problem with animals is that they have cannibalistic behavior. So they're more likely, if an animal dies in their herd, to eat that dead animal because they don't want it to go to waste. It's just part of like their nature because there's nutrients here and whatever. Whereas humans have like knowledge and wherewithal of like, if a sick human died, maybe we don't eat the sick human. And we also have the morals associated with just general cannibalism. So there's knowledge of hygiene, and then there's the morals associated with cannibalism that protects that from that being spread within humans, that animals don't have that, right? So that's where the issues come from there. It's a good question, actually. All right, so moving on. What is asepsis? Asepsis. And Duncan, you're going to give me an example of this. So asepsis, if we use something to perform asepsis, we often call it an antiseptic. So you can also think of that too, if that helps. An example of an aseptic or antisepsis. So this will help too. Asepsis is removal of microbes from animate surfaces or living tissue. So do you have an example of that, Duncan? Yeah, and you use like something to clean the cut, like, and this is very general. This is like obvious stuff. Don't overthink it, okay? So if you have a cut and you want to clean it with alcohol or hydrogen peroxide, that's an antiseptic. We're using it on living tissue. If you are prepping your patient's arm for an IV and using an alcohol swab, antiseptic. If you are prepping your patient's belly for a C-section using iodine, antiseptic. Asepsis. Those terms are usually, generally for our purposes in this chapter, interchangeable terms. Okay, asepsis and antisepsis. They're the same for our purposes. Makes sense? You guys following with that? All right. All right, what does it mean if a method is microbicidal? You guys know this stuff. All right. So Dylan, I'm going to ask you the other term. What is microbistatic? So cidal is when we kill it. Yes, exactly. And so when we're talking about microbicidal versus microbistatic, we're talking about microbes in general. We're talking about bactericidal and bacteriostatic. We're talking about specifically bacteria. Fungicidal, fungi. Virucidal, viruses. And it's otherwise pretty straightforward, okay? Sporicidal. Sporicidal means that it kills endospores. Okay, so actually talking about endospores with that, okay? So if something is sporicidal, it's generally also going to sterilize. Also point something else out. If something can sterilize, if it can kill endospores, it's probably also going to kill you. Just saying, generally speaking. Now, parts of your body might be able to withstand exposure to some aspects of those sterilizing agents, but generally it's really done to treat, to get rid of all of the endospores. It will probably also kill you also. We can't put your body into an autoclave, right? That would definitely kill you. Just saying, it would definitely kill you. All right, just pointing that out too. All right, so there's one here that also, I think this is the one that trips people up. Oh, yes, it is. Which one of these sterilizes? Yes, she did. Evelyn, you're going to be our next person. I don't know if I want to ask a question about this question. I'd like to stick with easier questions. Okay, so these are going to be dry oven and incineration. So boiling water is not going to sterilize. Endospores can survive boiling. If you're just boiling water, even if you're boiling it for an hour, You're not going to kill the endospores because 100 degrees Celsius is not hot enough to kill endospores. If you get it to 121 degrees Celsius, you'll kill the endospores. But water can't get to 121 degrees Celsius because it'll just boil and turns into gas, it vaporizes at 100. So how do we get water to 121? We add pressure. And so this was something that a student in my class, I don't know how they remembered it because I didn't. It's called Boyle's Law, B-O-Y-L-E'. And it's that idea of if you change pressure, you change the boiling point of something. Right? Now we learned that in chemistry. And so that's what's working. I couldn't remember what the law was called, but one of my other students remembered. So that's the idea. Yes. Yeah, don't worry. I will type it, yeah, when I get to it, but I want to make sure it's not too difficult. So I'm trying to make this one a little easier. Boyle's law states that basically if you increase the pressure, it increases the boiling point, okay? So by adding pressure to water, we can increase the temperature of that water, increase its boiling point. So we add 15 PSI, which is what we do in an autoclave, and that allows us to get water to steam at 121 degrees Celsius, and that will kill endospores. So that's what an autoclave does. Adds pressure so we can get the temperature up above to actually kill those endospores off. So boiling doesn't achieve that. It only gets to 100 degrees Celsius. And so what you can do though, is that vegetative cells, all vegetative cells, will be killed with boiling, just not the endospores. So what you can do is boil it for 30 minutes and let it cool down to like room temperature, and those endospores will wake up. And they'll be like, oh guys, it's free, we're good now. And you let it sit there for like an hour to 2 hours. Then you boil it again. And after all those endospores woke up and thought things was good, you hit them again with the boiling. And you can cycle that several times. If you're cycling boiling temperature and cooling it for a little bit, boiling temperature and cooling it for a little bit, that's called tyndallization. Okay. So some of us might be like, oh, when you cycle hot to cold, that's called pasteurization. It is not. It's called tyndallization if you boil. If you are sub-boiling temperatures, we're talking 60 to 70 degrees Celsius. Now, 60 to 70 degrees Celsius is pretty hot. So I want to point out to you that 100 degrees Celsius boiling temperature is 212 degrees Fahrenheit. You ain't gonna survive that for sure. But if we're talking 60 to 70 degrees, now what we're talking about is probably closer to, I have to do the math in my head, so you're gonna have to bear with me for that. It's like 150 degrees Fahrenheit, but 150 to 170, okay? I don't think you'd survive 150 degrees Fahrenheit very well either. So when I'm saying 70 degrees Celsius, I'm talking more about like 150, 160 degrees Fahrenheit, to put it in perspective. That's still pretty hot, but it's not boiling, right? So if we're keeping it sub-boiling and we are just treating it for a few minutes and then cooling it back down, and then a few minutes up and cooling it back down, that preserves the nature of the liquid, but helps get rid of the pathogens, because most of them aren't going to survive 150 degrees Fahrenheit anyways. So that process is called pasteurization. Okay. If you're using it more specifically to sterilize and we're getting to boiling temperature, that's tyndallization. So it used to be used to sterilize things. We don't really use it much anymore. It's very limited use now. But pasteurization is commonly used, right? So that'll be my question. This is an easy question, and you guys are going to hate that I'm not giving you the question. I'm giving it to Evelyn, okay? Evelyn. Oh, I'm having it on my iPad, like she's going to see that. Not even connected. Evelyn. My question to you is, give me an example of where we use pasteurization. Probably by the time that I type this, she'll have an answer. Okay, so you guys probably have it in your mind what it is. It's meant to be an easy question, okay? Obvious, everyday type of a thing, okay? So, beautiful, exactly. We knew it was coming. Okay. Yeah, beer making and stuff like that. It just depends on like what step in the beer and stuff like that. It helps reduce things like botulism and stuff like this. Not 100% obviously, but it does help with that. and with pathogens that might have come in from like the hops and the things that we add into the beer. But yes, so milk, obviously. Anybody in here have a particular milk brand that they like more than another milk brand? I usually in other classes have this. Do you have one that you like? Fairlife?
No, I was gonna say Fairlife or the Lactate brand.
Fairlife or the Lactate brand? Fairlife, the Lactate brand, and Brahms. There's another popular one that a lot of people like. Notice how it tastes fresher, those milks? You don't have an off taste to any of them. If you haven't drank one of those brands, you are missing out, I promise, okay? They are all ultra pasteurized. And you'll also notice that those brands also last forever on the shelf, like say on the shelf in the fridge. Still, you have to still refrigerate them. They are not sterilized, but they're ultra pasteurized. So that means higher temperatures for longer. It kills off more of the microbes. If you want to live that weird, I don't mean it that way. If you want to live a different life than I would choose and drink raw milk that is unpasteurized,
It's okay.
I do not recommend it for reasons of anthrax, tetanus, botulism, E. coli, and listeria. You want to roll the dice with that stuff? Live your best life. Right. That's how I feel as well, especially as somebody that has worked for a while in food industry. That's how I look at it too. It is like playing Russian roulette with a loaded gun. So unpasteurized raw milk, yes. So if you're drinking regular pasteurized milk, I'm not poo-pooing on that. If it's pasteurized, you're fine. If it's ultra pasteurized, I just like it better because it lasts longer and it tastes better. It's a preference thing, okay? I also don't drink a lot of milk. It's just me and my husband. I don't have kids. My first husband came from a Catholic family. They're a very big family, okay? Genuinely like traditional Catholic. And so they had a gallon of milk out, and that's what you drank with your dinner was milk. And I hate milk, guys, okay? And I hate it. And so I will have milk with my Oreos, or if I randomly have cereal, and if I make hot chocolate, I make it with milk. That's the only time I really ever have milk. Or if I'm cooking with it, like making queso or something like that, okay? That's really the only time I don't drink it. I don't like how it tastes like that. So I don't drink a lot of milk. So if you are also somebody that like you sometimes have milk or you have it like in your coffee or something like that, and you find that you waste a whole gallon or a quart of milk or something, buy Fairlife, buy Lactate, because they will last months, quite literally. And I mean, they're still fresh. And some of us have a trepidation. We'll open that Fairlife and it's like, it's good until January. Yes, it is, even after you open it. And I mean, just trust me. It's, yeah. So if you don't drink a lot of milk and you feel like you waste money on milk, buy one of those ultra pasteurized brands. They last so much longer.
You're giving my unvaccinated kid raw unpasteurized milk. I'm like, do you want them to die? Like, do you want them to be gone?
Yes, so whatever. All we can do is educate people, right? So that's how we will look at it. Okay, so moving on, let's go on. All right. All right, which of the following choices here sterilizes? So Kaylee, you will be my next person. I'll type your question in the chat as well. I'm gonna ask you, Kaylee, I don't want to make this one hard either. Give me an example. I'm typing it in my iPad again. Example of ionizing radiation. Okay, so ionizing radiation can sterilize. Autoclave obviously can sterilize. Now, traditionally in our list of what can sterilize and what can't, traditionally we would say UV radiation is not typically used for sterilization, but can it sterilize? It can, but there's really specific circumstances where it can. So usually if I'm asking on the test, which one of these can sterilize, I'm not going to put UV radiation in there because it is sort of like in a very gray area. Okay, so I'll try to keep that one kind of very, not make that weird, okay? But I might ask you about how UV radiation works or what type of radiation it is. So UV radiation, when I ask my other classes, I was like, what type of radiation is UV radiation? And my other class says, ultraviolet radiation. And I was like, okay, well, you're not wrong. But that's also one of the things that relates back to one of the questions that people are getting wrong on the exam, right? Yes, microwaves, X-rays is probably the better example of one of the ionizing types of radiation. So absolutely will work for that. Okay, so for UV radiation, it is non-ionizing radiation. So that's really what I was looking for when I asked my other classes and why I didn't want to ask you guys. So what happens is with, my brain decided it was done. What happens with ionizing radiation? We have energy waves, usually associated with some sort of particle there, that will disrupt the electrons in atoms and cause them to shoot off. When we say it's ionizing radiation, we mean it's literally making ions. You remember ionic bonds, right? And how an ionic bond is when an electron is transferred from one atom to another, like with sodium and chloride. Sodium donates its electron to chlorine. So sodium now is Na plus, and chloride is now Cl minus, and that's what table salt is as an ion, okay? So ionic material. That's literally what ionizing radiation does. And so X-rays is a very baby version of that. X-rays can be blocked by lead. Gamma radiation cannot, okay, especially higher level gamma radiation. And in fact, you can have some of these atomics that are, I'm going to walk away from the screen, but you're not missing anything really, I promise. But there's a periodic table of elements over here. Polonium, astatine, radon, heard of it at least, right? These guys that have these symbols on them here. Plutonium, right? That sort of stuff. These guys that have these atomics, this means radiation on it. It's this little circle with the round triangle, round triangle. That means radioactive. So that's so that if you ever look at this and you're not really sure what you're looking at. I like this one because it has the ones that are radioactive on here. Uranium, obviously, okay? So we're talking about radioactive elements. What we mean is that they decay. They have ionic decay, or they have some, either they're shooting off at some point, sometimes even they will lose protons and stuff like that. So if they lose enough electrons, eventually the protons don't want to stay associated with the atom. So they can actually lose protons. And so we can actually have decay of something like uranium into lead. It can actually change what atom it is, because we have enough decay of electrons and then decay of protons. We can actually decay into a whole other type of element, which sounds like alchemy, but it's real. And so that happens over a long period of time. It's actually where we think all of the lead on Earth came from, was from radioactive decay. Pretty interesting stuff. It's really interesting, actually. So you can talk to Dr. Tim about that if you're interested in it. But the idea is if I can take uranium and enclose it in something that keeps those radioactive things from shooting out, all that radioactive energy in there, and it's just going to compound on itself if you let it go. And that is what atomic bombs do. So we're concentrating something that wants to release that radioactive energy and keeping it contained. And then we're dropping something in. And so what my chemistry professor did was he said, basically, like, imagine that I slapped you in the face. And then you reach out with 50 hands and slap all the people around you. And then they slap all the people around them. It's a cascade, right? One person slaps, and then one person slaps 50 people, and then all of them are, whatever. Everybody's slapping everybody. And that's what happens in an atomic bomb detonation. So we're holding everybody's hands back, and then suddenly we're slapping one of them. And then that just causes an instantaneous, almost cascade of everybody all at once, releasing all of that gamma radiation. And it happens so fast, it creates a physical response in the matter around it that can literally vaporize bodies, quite literally. And that's radiation that did that. It's not fire. The heat and stuff like that is created because of how quickly and how much radiation is being released, and all these atoms releasing all that energy. The heat is a byproduct of the radiation itself. So you can actually have so much damage so instantaneously from radiation, it can literally vaporize your own atoms, basically. Now that's extreme levels of ionizing radiation. You walk yourself near something that's less extreme, but still very, very deadly. The elephant's foot of Chernobyl. which is like where the decay is still actively happening in the reactor in Chernobyl. You go there and you will probably die within hours if you don't have any protection on whatsoever, right? And that's because all the radiation is causing your own atoms in your body to release electrons. Well, you're not meant to have ions in your carbon and hydrogen there. And so now suddenly your cells can't function the way that they're supposed to because the chemicals that make up your cells are messed up because they had to ionize because of all this radiation. So ionizing radiation literally ionizes the chemical makeup of organisms, including bacteria and things like that. So we can use lower levels of gamma radiation and X-rays to kill microbes. Now, I'm not going to gamma irradiate you to eliminate your microbes, but I could gamma irradiate you to eliminate some of your cells that are more delicate, like maybe your bone marrow, or any cells that you have in your body I can target radiation to in order to kill a tumor, something like that. Is it dangerous for other cells? Yes. But if you're going to die from the cancer anyway, is it a risk that some doctors are willing to take or that you might take? Yes. We can target radiation to specific areas of the body to kill targeted cells as well. But more commonly, we see radiation on a day-to-day basis. Anybody ever opened a container that had plastic and paper on one side and you open it up and you get something plastic out of it? No, anything ever. You open like a Vacutainer needle. You open a needle container. You open any package that you've ever bought at a store where it's like a medical thing and you open one side that's paper and the other side was plastic and there's something in it.
Yeah.
Band-Aids. That was irradiated. And we keep the paper around there to make sure that what's in it, microbes can't get to it. But did the paper get damaged by the gamma radiation? No. And all that plastic and stuff in there that would normally get melted or ruined from autoclaving and the heat associated with autoclaving, or might even get ruined by the moisture from autoclaving, or might get destroyed from being exposed to a dry oven. Those things now can be sterilized with cold sterilization, which is what most ionizing radiation that's used in the medical field will do. Not all of it is going to create the heat that we see associated with an atomic bomb, right? If we're using lower levels of it that destroys cells normally, then we are going to be using it for those disposables that can't be autoclaved, right? So a lot of times needles, Vacutainer systems, Band-Aids, sterile gauze, all of those things that you open up the package, it's very satisfying. But what's in it is sterile because of ionizing radiation, cold sterilization. So very, very commonly used in the medical field, yeah? And so you probably didn't even think about it before, but that's how that stuff got sterilized. Pretty interesting, right? All right, so that's that. UV radiation, like we said, is non-ionizing radiation. And most of the time we see it naturally coming from the sun. And so what happens is the ultraviolet radiation, which is literally like light particles moving at a certain wavelength. That energy causes DNA to bind differently than it should. So I'm going to draw this one. I always forget this doesn't work the way that I want it to. If you had a DNA sequence that was A, T, T, C, G, A, whatever, and across from it would be T, A, G, C, T, right? And these guys are hydrogen bonded across to one another, like this. So this is your DNA. And yes, okay, 5' to 3', and 3' to 5'. And that's what makes them anti-parallel, okay? We tracking? All right. When we have non-ionizing radiation, what happens is the energy comes in and it causes the T's to covalently bond to one another. So now they're not going to bind to the A's across from them. This is a problem because when your cell needs to divide and we separate the DNA strands, now it can't get the A's that match up to bind with the T's because the T's are preoccupied with each other. These are called thymine dimers. Your body has a system in place that if we catch it at a certain point in your cell's lifetime, we can actually cut out this BS and replace it according to the fact that you still have A's across from there and replace it with the proper T's that are no longer covalently bound. We have to cut out the DNA and literally add in the T's again, new T's, fresh T's that aren't covalently bonded to each other. If you don't catch it in time now, if your cell is going to that point where now it needs to replicate and we've already split the DNA apart and we didn't catch it in time, then if you're trying to copy that strand, you won't be able to. Or your body will try to compensate and be like, I don't know what's supposed to go here. Let's put a G. And suddenly things like single nucleotide polymorphisms, which would lead to an improper amino acid, which would lead to your protein misfolding and potentially being catastrophic to your cell, could happen. So those are mutations that can result from non-ionizing radiation. So if your body sees this a lot, if it sees these weird T's and it needs to cut them out and replace them, your body also says, this guy keeps putting us in UV radiation. We need to make something to protect ourselves. Let's have these cells that are having this issue make melanin. And melanin will absorb that UV radiation so that we don't have thymine dimers happening again. Now, it protects to a degree. And obviously some races of people have more melanin naturally than other races of people. And that tends to be races that live in tropical areas for a reason, right? And so it makes sense. And so there's that. But also it only protects to a certain degree. At some point, you will have enough damage done to your DNA that you will have some of these mutations show up. And if it happens in certain places, or if it happens at certain points in the cell cycle, then we can see cancer developing. And that's how we get things like melanoma. So UV radiation causes this, thymine dimers. And it does the same thing in bacteria too. If you cause enough thymine dimers in bacteria, then they won't be able to replicate either. So that's how we can sterilize. Now, it takes 30 minutes to an hour of exposure to UV radiation to sterilize something, okay? But it only sterilizes the surface. It can't penetrate. It's very bad at penetrating. In fact, even some glass can block UV radiation. So it's not very good at sterilizing, which is why we don't typically consider it to be a sterilizing method, because it's not commonly used to sterilize, because it can't penetrate at all. So if I have my hand out like this and my hand is absorbing the UV radiation, anything underneath my hand is not going to get sterilized. That's a big problem. So we don't usually use it for sterilizing like that. It's not as effective. Make sense? Everybody tracking on that? Cool. All right, let's move on. Next question. There are no liquid cleaners that can achieve sterilization. It's true or false? Are there any liquid cleaners that can achieve sterilization? We're going to get into the type of chemical cleaners in a moment. And to get ahead of that, I'm going to ask some of you guys to give me examples. If my iPad will wake up, there it goes. All right, so there are liquid cleaners that can achieve sterilization. We're going to talk about some of those in a moment. In the meantime, to prepare for that discussion, Jessica, you're going to give me an example of a halogen.
Chlorine.
Sure. All right. So chlorine is the example that she's perfect. Good way to be on top of them. Julacey, you're going to give me an example of, it always gets harder after halogen. Phenolic. You might have to look it up. So I'm going to give you a minute to cook with it, okay? Phenolic. I'll actually write it up here so you can see the word, so you can know what to look for. You're going to give me an example of a phenolic. I don't usually ask people to give me an example of an alcohol because I feel like that's too easy. I'm just saying, I like you guys, but that's a little too easy. So we'll be talking about the halogens. We'll be talking about the phenolics. We'll be talking about the alcohols. We'll be talking about the aldehydes. And Tonya, can you give me an example of a specific aldehyde?
The phenol is carbolic acid.
I will take it. Carbolic acid. So we'll get into that in a little bit. So we're just dipping our toes into this. Don't think too hard about this, Tonya, because it's probably more obvious than I'm trying to make it sound like it's not going to be, but it is meant to be slightly obvious. Okay. Of course, it's fine. It's fine. We'll take it. Don't overthink it. Formaldehyde. All right. And I'm trying to think if there's another one I want to ask about, but I feel like this is fine. We'll start here. Okay. So we'll talk about the aldehydes. The chapter also talks about like the heavy metals, and it talks about the acids and the bases as well. So, oh, an oxidative example. Let me see who our next person is. Someone give me one. Jonathan, you're our last person. Jonathan, you're going to give me an example of an oxidative. Oxidative, so that you can look that up. Okay. All right. So we're going to get into quite a few examples of these. Remember the contacts yellow so you can get her makeup stuff done. So phenolics. Well, actually, let's bring it back to the halogens. Start with the halogens, and our example was chlorine. All right, so anything based in chlorine would fall into this category. This includes bleach, but it also includes things like chlorine dioxide, which we pump through our drinking water in order to make it drinkable. It also includes the chlorine that we would be adding to our pools to help them stay disinfected and stuff like that. So bleach falls into the chlorine category. Most of our halogens can sterilize at the right concentration and if used in the right situations for the right amount of time. Not all of us do that. And often if you're using like household bleach that's diluted according to the back of the packaging, it's usually more of a disinfectant, but it is very effective. So I want to be very clear about that. It's a very effective disinfectant, but it can be sporicidal if it's used appropriately. So if you're just cleaning like your bathroom floor and you don't have a lot of debris or you don't have a lot of like other liquids that you're trying to mop up with it, then it can actually sterilize if you're keeping it wet with the bleach long enough. So you're actually exposing, most of us just kind of wipe it on there and wipe it off. It'll disinfect, but if it's kept wet for long enough, it can actually sterilize if it's done properly. So that's the take back with this. Another problem with the halogens is that they're pretty heavily affected by organic matter. And what I mean by that is blood, pus, urine, feces that we might be cleaning situations with. And so those things can also affect the effectiveness of this. These chemicals can react with those things and then be less effective, or they can be watered down or diluted by those things, making them less effective, right? Okay. Okay, so chlorine, bromine, iodine, another obvious one that we use commonly in the medical field, right? So iodine is a halogen, and then another one is fluorine. Fluorine, we see it as fluoride in toothpaste. Now, again, very heavily disturbed by the presence of organic matter. And this can even include the goo, the sticky stuff, the slime layer or the capsule associated with biofilms. So that can affect the effectiveness of fluoride, which is why we don't just put pure fluoride on your teeth. We have you brush your teeth with a sudsing agent, a detergent. The detergent helps break down the biofilm. So now the fluoride can actually act on the bacteria and kill them. It's also why we need to floss. Because if you don't break down the biofilm between your teeth, the fluoride can't actually work on those bacteria very well. So, makes sense? Okay. So those are the halogens. Phenolics. Phenolics are anything based on carbolic acid. So carbolic acid itself is actually phenol, propophenol, which if you don't remember phenol from organic chemistry, OH group, okay? That's phenol. Anything based off of this structure is known as a phenolic. Probably the most common phenolic is going to be chlorhexidine. Does it have chlorine in it too? It does, but the more effective aspect of it is the fact that it is a phenolic. It's based off of phenol. Chlorhexidine is commonly used in the medical field. We often use it if you need a clearer prep site than what you would need with just alcohol prep. So if you're starting a central line, you might use iodine or chlorhexidine, okay? If somebody is allergic to iodine and you know that ahead of time, then you might not use iodine to prep their skin or something like that. You might use chlorhexidine. Chlorhexidine is actually more effective than iodine and usually less toxic than iodine. However, you can be allergic to either of them. And so that can be a big problem too. If we're just doing a surgery and we're going to put iodine on you temporarily and then move it off, we usually aren't going to be worried too much about that. But you're getting a iodine contrast for like a scan or something like that, then we don't want to pump you in with iodine. If you're allergic to it, that can be a problem. But chlorhexidine is a good alternative to that. You guys know about how doctors scrub in for stuff. And if you're going to be a surgical nurse, you might have to scrub in to a surgical site. We're talking 2 minutes straight of scrubbing. Are we using detergent with that? yes, detergents, we're using surfactants, often based on quaternary ammonia compounds, but we're also incorporating within that chlorhexidine. So chlorhexidine is there also. It's more effective because the detergent is there and it works with the detergent. So we've got the phenolic action, but we've also got the detergent surfactant action as well. 2 minutes straight of scrubbing with that. The most common surgical scrub, the most common chlorhexidine product that you're ever going to see in the medical market is going to be Hibiclens. Very commonly used. There's Hibiclens and there's another one that I can never remember the name of it. Provone or something like that. Can't ever remember the name of it, sorry. But they're available over the counter too. But they're commonly used as our surgical scrub agents for that. You will absolutely see it when you work in the hospitals. You probably have seen it and never realized it had chlorhexidine in it. So those are phenolics. Our aldehydes, formaldehyde, glutaraldehyde. Okay, I can spell. These guys are very toxic, but they are sporicidal in the right concentrations. We use them in appropriate strong concentrations. They should be sporicidal. But however, the more sporicidal that you get with glutaraldehyde or formaldehyde, the more toxic it is to the people that are handling it. Glutaraldehyde tends to be more effective than formaldehyde. Formaldehyde tends to be more toxic. You get higher concentrations and it's much cheaper to work with formaldehyde. So it just is kind of depending what your application is and stuff like that. If you're preparing a body for a viewing or something like that, we usually reach for glutaraldehyde. If we're preserving the body long-term for something like dissection, we're usually going to reach for formaldehyde. And so it'll last a little bit longer, but it is also more toxic as well. The aqueous or water-based version of formaldehyde is called formalin. So you've probably heard of that as well. All right, another aldehyde that we also hear of is OPA, and you're going to bear with me. Ortho, I have to say it out or to be able to spell it. Ortho-phthal-aldehyde. You are welcome. Okay, there it is. I will not ask you to write it out on the test. You're also welcome. Okay, commonly referred to as OPA, ortho-phthal-aldehyde. And ortho-phthal-aldehyde is an aldehyde that is much less toxic, but also is not sporicidal. It can't sterilize. So it just depends on what application we're talking about for the aldehyde in that situation. Okay. Jonathan, did you ever find an oxidative one? Thank you. Perfect. H2O2, also known as hydrogen peroxide. If it's oxidative, anytime you hear the word oxidative, we are talking about redox reactions. What do redox reactions have to deal with? Electron exchange. Okay, so something is losing an electron and something is gaining an electron. And H2O2, we already know that hydrogen peroxide, H2O2, is a reactive oxygen species. We've learned about it previously. So this is a reactive oxygen species that we're using to our advantage. Any organism that can survive being in oxygen has to be able to deal with reactive oxygen species. So H2O2 is better used against things that aren't dealing with H2O2, so our anaerobic things. If you have a deep tissue wound, we'll often irrigate with hydrogen peroxide. The problem is at high concentrations of hydrogen peroxide, it's also deadly to your own cells. Your own cells can only accommodate so much hydrogen peroxide. Your over-the-counter hydrogen peroxide is 3%. 3% is disinfecting. Anything greater than 6%, we usually actually use it at 35% more commonly, we can actually sterilize. 35% we will actually vaporize. You'll have 35% vapor in the air of hydrogen peroxide, and that can actually be used as a chemiclave. So we can put instruments that can't withstand heat and that we might not want to ionize for whatever reason. And so we can actually sterilize with that, like a chamber. I guess we call it a chemiclave because it's like autoclaving, but without water, we're using a chemical. Okay. All right. So that's at greater than 6%. We're usually looking at 35% for that. You're at 3%, which is your over-the-counter hydrogen peroxide in the brown bottle. That's just going to disinfect. Okay. And it causes like tissue damage as well. So if you're using it a lot, you're risking tissue damage. It can actually make some infections worse, depending on what the infection is, because you're actually feeding the infection with the dead tissue if you do that. So depends on what is going on with your patient and whether or not that is an appropriate treatment for them. Generally speaking, for open cuts and wounds that you're getting at home, that you would treat at home, you don't need to be using hydrogen peroxide for it. Is it good for rinsing your mouth out as a mouthwash? It's excellent because many of the anaerobic bacteria that are in your biofilms can be killed with the hydrogen peroxide. So it's usually pretty effective for that. and also whitens your teeth naturally. Another one, alcohols. Alcohols include obviously ethyl alcohol. Or isopropyl alcohol. Okay, do you guys remember in organic chemistry or GOB, whatever version of it you took, would have been GOB for most of you? You remember methyl, ethyl, I hear whispers. Methyl, because this is how I remember it too. Methyl ethyl propyl butyl. I used to say it over and over again before my exams for organic chemistry so that I wouldn't forget. Methyl ethyl propyl butyl, methyl ethyl propyl butyl. And that's how I memorized them. And if you ask me about how many carbons does ethyl have, I'll be like methyl ethyl propyl butyl, 2. That's how I will think about it, okay? Methyl has 1 carbon, ethyl has 2, propyl has 3, and butyl has 4. That's how many carbons they have, okay? This is in organic chemistry. That's why methane is just C with H's all around it. A and C, we know it always makes 4 bonds, okay? So ethanol, OL means alcohol, okay? OL, that aspect. So if we have ethanol or ethyl alcohol, we know we have an OH group on it. So ethyl alcohol, quite literally, is just 2 carbons with an OH group on them. And then you fill in H's in all the spots that you have a carbon. It's really not that hard. There is ethanol, okay? If we're looking at propanol, propyl alcohol, okay? Propanol, then you have 3, C. If it is iso, this also means 2 propanol. This means that the OH group is in the middle, because you could also put the OH group on one of the end carbons, but that's not what we're having with iso. In iso, it is isometric. It is an isomer. So we've got equal things going on the outside of it. So that means that the OH group is in the middle. Then you just put H's out here. Make sense? Okay. It's the fact that we have these carbons and hydrogens that lends to the effectiveness of these alcohols. The fact that we have carbons and hydrogens around here interacts with things that tend to be hydrophobic, and then the OH group tends to interact with things that are hydrophilic. So these are semi-amphipathic, sort of like our phospholipids are. So these tend to work really well on membranes, naturally, but they also can affect cell walls. And at the right concentration can actually coagulate proteins. These are pretty effective at how they work. Now, at what concentration do alcohols work best? 70%. This is because the water, the H2O, the other 30%, that the water aspect helps coagulate the proteins. So the alcohol and the water together at that concentration will coagulate the proteins. This is why if you ever go to CVS and you're like, oh man, I need an antiseptic to clean a wound or something like that, and my kids always scrape their knees, what should I clean it with? 70% alcohol. Now, isopropyl works the best. If you're using it regularly, like with hand sanitizers, and you're using hand sanitizers all the time, like we were during COVID, constantly using hand sanitizer, all right? They have now changed that alcohol to be usually ethyl alcohol, because the ethyl alcohol, it evaporates slower, and so it's going to cause less drying out of your skin. But isopropyl alcohol, because it dries faster, actually helps to kill the bacteria faster too. But if you use isopropyl a lot on your hands, your skin dries out faster, you get cracking of your skin, and then you're exposed to microbes. It's defeating the purpose. Okay, make sense? So the one that we actually prefer for asepsis is isopropyl, but if it's for routine use constantly, then we would prefer to reach for ethyl alcohol. So it kind of depends on the thing. If you guys are prepping arms for IVs or needle sticks or for collecting tubes or something like that, and you're almost always using the prep pad with isopropyl alcohol on it because it's more effective and it dries faster. If you don't let it dry all the way, it's not effective. So you have to let it dry. If you ever are a patient or watching a patient get stuck with a needle and the person prepping the arm doesn't let it dry, you can let their infection control officer know about that. Because you have to let it dry for it to be effective. You learned from the best, okay? All right, so we're gonna move on. True or false? Isopropyl alcohol is preferred over ethyl alcohol for asepsis. We're talking about most effectiveness here. We'll leave this up for a little bit. We're almost done with this chapter. Some bug just landed on my face. All right, so this is true. Thank you for paying attention, guys. Good job. All right, on to the next question. We're gonna kind of like rock through these. Which of the following is not a halogen? Kind of have the halogens written up here, so I think that should kind of help answer that question. So, the gases. This will include chlorine dioxide, okay, which is a chlorine-based compound, but it's also gas, okay? But this new gas is ethylene oxide. Yes, ethyl, ethylene, ethyl. It looks like this, okay? Like quite literally, it would look like this. And we know that there's a carbon here and a carbon here. And we know that these carbons are attached to hydrogens. Looks like some sort of Illuminati sort of like symbol, but it is ethylene oxide. It's carcinogenic, it's toxic, it's explosive, it's combustible. It's like super dangerous. But I could pump a room full of it and it'll sterilize everything that the gas gets into. It's very effective. It's actually what the CDC uses to sterilize their BSL-4 labs. So as they rotate from lab to lab, they don't want to work in just one lab because it gets contaminated with Ebola and things like that. So they switch labs every now and then, and they pump the whole room full of ethylene oxide and then let it sit like that. And then they'll switch to a new room. When they go in and out of the rooms, they get sprayed down with a hot chemical, and that chemical is usually carbolic acid. So it's actually pretty effective at that as well. So that prevents the spread of that. The suits that they wear in those rooms, by the way, have air pumping into them so that they always have positive pressure, so that if it gets a tear in it, microbes won't be likely to get into the suit. They'll be blown out of this. So that's how those suits work too. Pretty interesting stuff. I got to tour it when they were building it, so it was really neat. All right, next. Multi-select. From these choices, which are the most difficult pathogens to eliminate completely? Now, of course, I want you to pick the one that's the most difficult to eliminate. And I messed up when I wrote the question, so you're going to get to hear me blab about that. Just pick one, yeah. I mean, I know it's multi-select, but like, just pick one. Because really one is the right answer. So this is endospores, and I accidentally clicked gram-negative. It's supposed to be endospores here. So the way that this works typically is prions are the worst of the worst, but they're not even living organisms. It's just a misfolded protein. Of the living organisms, endospores by far, by far. Then we have the acid-fast guys, which are gram-positive. That's Mycobacterium species. Then we have some gram-negatives and some gram-positives. It just depends. There's mix and match in there, okay? Vegetative bacteria, we'll say generally, okay? Then we have like the Mycobacterium gram-negatives, which don't have the wall at all, okay? Then we have the non-enveloped viruses like polio. Then we have the enveloped viruses like flu, stuff like that. Okay. So that's generally how the setup is worked out. And that in between stuff with the gram-positive and gram-negative vegetative cells, it's just really hard. It just depends on the microbe, really honestly, in there. So there's some mix and match going on in there. But endospores by far. So when I made the question, I messed up when I clicked the choices. That was me. All right, how do surfactants work? All right, so this is your phospholipids that make up your lipid bilayer, right? All right, the way that surfactants work. Most of our surfactants are going to be what are known as quaternary ammonium compounds. They're quaternary ammonium because there's literally a nitrogen with 4 things bound to it. Usually most of them are H's. These are all H's around it, okay? And then it's attached to usually a long tail. Hydrophobic tail. Here, when nitrogen is bound to 4 things, it has a positive charge to it. What happens is that all of our phospholipids here, all these heads, are negatively charged phosphates. And they'll hang out with each other because they'd rather hang out with each other than with those nasty hydrophobic tails. But you introduce a positive to the group, they're like, oh, hey, girl, we ain't seen you. We've been waiting for you all day long. It's like a bunch of single guys that had to hang out with each other because there was no girls around, but now there's a girl around. And it comes in with this little positive charge here, and it is more than welcoming. But the problem is it doesn't quite fit in the space quite right. So what happens is it causes openings in the membrane, causes the membrane to leak. So it basically intercalates is the word for it, okay? But it squeezes in between the phospholipids and pokes holes in the membrane like that. They also can bind with dirt and debris and the microbes themselves and make them separate from being attached to your skin and your tissues and things like that, or to tabletops or whatever. This is how most cleaning agents that we see that are not chlorine-based work. So those usually got some sort of quaternary ammonia compound in there, okay? So many of them are surfactants, and all detergents are based on surfactants. They just also have other ingredients to help with the decontamination process in it as well. So for our purposes, a detergent and a surfactant are kind of the same thing, because the whole reason that a detergent is a detergent is because it has a surfactant in it, but it might have other things with it too. Okay. Any questions about the surfactants? Okay. There's a little podium really quick. And we're going to really quickly walk through our exercise so we can move on to the next thing, finish up. Bob, let it load up the next game. And we'll do chapter 11's activity thing. We'll walk through it. We've covered most of the concepts in the activity, so I think we'll be. Full this one. Okay, so chapter 11, activity, it talks about quaternary ammonium disinfectants and antiseptics, tolerance, resistance, and potential impact on antibiotic resistance. So this is talking about benzalkonium chloride, which is a quaternary ammonium compound. You might not have known that. It's very commonly used as a topical antiseptic, benzalkonium chloride. It used to be that if you got your ears pierced at Claire's, they gave you a big old bottle of benzalkonium chloride. And I actually still use benzalkonium chloride based skin treatments when I get piercings, but not like heavily. Only whenever like I really have some sort of shit going on with them. But anyways, doesn't matter. Boring for you guys. All right. So it's talking about quaternary ammonia compounds. What aspect of the cells do quaternary ammonia compounds affect? The membranes, okay? And interferes with the membranes. If they can't sterilize something, why would we even use it in healthcare? Because you can't always sterilize everything. Like I said, if it sterilizes, it's probably damaging to the patient. So this is useful because it's non-toxic to the patient, around the patient, and for the person that's actually handling the cleaner as well. It's pretty non-toxic. And we also usually combine them with other chemicals like chlorhexidine, and that makes the chlorhexidine more effective. It makes other chemicals able to penetrate into things. In microbial control, tolerance refers to microbes being able to transiently survive lethal treatment with antimicrobial compounds, whereas resistant means you have a heritable trait that lets you survive. Why is it important to know the difference? Well, you might think that you're cleaning a surface and that it's able to, that you're getting rid of everything on that surface, and something transiently survives. That's sort of what we would consider to be a fluke thing. But if it's actually able to, for heritable reasons, able to survive that situation, then it can pass that on to other bacteria and spread the resistance. And so that's a bigger issue where we would be more concerned about resistance than we were about transient tolerance. That's the issue there. What are consequences of improper dilution or improper application of our disinfectants? Obvious one here, right? If you don't have the right concentration of a disinfectant, you're not killing as many microbes as you think you are, and you're leaving some behind, right? So that's a big issue there. If you're using bleach, but there's a lot of poop in that area, if someone poops a whole pile of poop and you're just like, pour some bleach on it, is that really getting to the poop underneath the pile? No. So stuff like that. I mean, it seems obvious. That's an extreme example, but obviously there's gray area in there too. You're missing some of the microbes. You're leaving them behind. You're putting your patients at risk for exposure. Biofilm associated bacteria, why might they be more difficult to treat? Is because they have multiple layers of bacteria, and some of our treatments might only get to the surface. So we have to break apart the biofilm somehow in order to get to the microbes that are there. Just like we talked about with brushing our teeth, right? That surfactant aspect of our toothpaste breaks down the biofilm so that the fluoride can actually act on the microbes in that environment. All right, we good with that? Everybody good with that activity? Walking through our application exercise there. Okay, moving on. Double check that we're signed in if you're still with me. All right, let's go through this. Chapter 12. If there's ever been a flashcard chapter, it's got to be chapter 12, okay? All right, first question. What is selective toxicity? Good job, guys. All right, so this is where we want to cause the maximum damage to the microbe, but minimal damage to the host. So basically max toxic to the bad guy, to the pathogen, and then minimum toxic to the patient, right? All right, that's the concept of that. Now, therapeutic index is a ratio between things. The ratio between the effective dose and the toxic dose. I'm gonna give an example, okay? If you have to give 5 milligrams of amoxicillin for it to be effective, which you can calculate with your Kirby-Bauer assay and that zone of inhibition and the minimum inhibitory concentration. Okay, so we get to that and it says your patient needs 5 milligrams of amoxicillin. But at 100 milligrams, it becomes toxic to people for whatever reason, okay? The ratio between this of the 5 milligrams is where it's effective and 100 milligrams is where it's toxic. That ratio is the therapeutic index. It's the actual, like, you divide the numbers. The closer those numbers are, so if you have a drug where, I don't know, 98 milligrams is effective versus 100 milligrams is toxic, ooh, that's very close. The closer you are to 1, the more dangerous that situation is going to be for your patient. Okay. If you're above 1, you got a real problem. Okay. So that's the therapeutic index. The therapeutic window is the actual difference. I'm just put quotes here because it's the same. The difference between the effective dose and the toxic dose. So our therapeutic window with our first example is 95 milligrams. Make sense? The therapeutic window for our second example, B, was 2 milligrams. Okay, so those are what those terms are referring to. I just wanted to clarify them. They're obviously very related, and they depend on the selective toxicity aspect, that concept. When we start using numbers, we're talking about the therapeutic index or the window. If it's the ratio, it's the index. If it's the window, that's the range, the difference. We good? Select all that apply. What types of organisms do antibiotics treat? There's some terms in this chapter that we're going to hit up real quick. So, antimicrobials refers to any microbe. Antifungal, fungi. Antiprotozoal, protozoa. Antiviral, viruses. Antihelminthic, helminths. Antibiotic, bacteria. Don't ask me why, okay? It's just what science has done to us, okay? But antibiotic, you're not going to hear, if we're talking about an antiseptic like a hand sanitizer being antibacterial, then we can talk about that in terms of microbial control. But when we talk about the drugs, for some reason, they're antibiotics, okay? I'm sorry, that's just the way the life is to us, okay? So just focus on the anti-B and then remember, oh, anti-B, that must be antibacterial, please, okay? All right, bacteria only. All right. Which antibiotics affect the cell wall? I cannot tell you how many questions like this you're going to have on that unit 4 or unit 3 test. There's so many. Cell wall here. I'm going to try to post sometime before the end of the week. I'll post a list of all the antibiotics that I expect you to know. But it's a lot. But we're going to go through the groups, okay? Ones that affect the cell wall. The Penicillins is a specific group, and other beta-lactams. So actually, let me actually erase this. I'm going to say beta-lactams. Penicillins fall into that group. So within the beta-lactams, we have the Penicillins, penicillin, ampicillin, amoxicillin, all of methicillin, all of them fall into this category. Okay, Penicillins, cephalosporin, and carbapenem. All of those are beta-lactam. Okay. We also have other things that affect the cell wall, like vancomycin, bacitracin, and isoniazid. Obviously, vancomycin is a very toxic antibiotic that we only reach for if you're resistant to other antibiotics that affect gram-positives, usually methicillin or anything weaker than methicillin. That's why we have MRSA, methicillin-resistant Staphylococcus aureus. What's stronger than methicillin? Vancomycin. But what's more toxic than methicillin? Vancomycin. It's very toxic to our patients. We almost exclusively give vancomycin under medical supervision. We usually have to be sure that we have reached a trough, meaning that that patient has basically cleared the vancomycin out of their system before we release them from the hospital because it can be so damaging to their system. Okay, but vancomycin affects the cell wall. Okay. We have ones that affect the cell membrane. These guys are going to be polymyxin and daptomycin. Daptomycin is also useful for biofilms. Ones that affect folic acid synthesis. These are going to be the sulfas. I call them the stinkies. They often have sulfa in their name or meth. And I'm not saying that people that do meth are stinky. Okay, they probably are. But what I'm saying is like methane is a stinky gas. And so that's how I think of this, okay? So sulfur is stinky. I think we are all agreeing on that, right? Methane is also stinky. So I think of that. So sulfamethoxazole has both sulf and meth in it. Stinky. Trimethoprim has trimeth. 3-meth, that's stinky, okay? That's sulfa or meth in it. It's probably going to inhibit folic acid synthesis. So sulfamethoxazole, silver sulfadiazine. Sulfur. It also has silver in it. Our heavy metals are antimicrobial as well. It's got 2 things going on for it. So those are our more common ones. All right. Things that affect, did so well some folic acid. Let's do DNA or RNA. Usually with DNA, what I'm talking about is replication. With RNA, we're talking about transcription. These guys affect helicase. Helicase unwinds the DNA. If you can't unwind the DNA, you can't open it to make any kind of copy of it, not an RNA or a DNA copy of it. So if we inhibit helicase, we inhibit that, okay? So the helicase inhibitors fall into a group called fluoroquinolones. Nope, that's a G, that's not a Q. Drugs that fall into the fluoroquinolone family end in floxacin. Levofloxacin, ciprofloxacin, those drugs, okay, floxacins. Fine. You can take a break and lay down. You just lay down and take a break. Okay. Are we're adult enough?
Yeah.
Yes. Okay. We're good. We're all good. All right. Yes, you're fine. Why don't you lay back here? It's a little more private where people can't see you. Okay. She's going to have a seizure. She is prone to seizures. It's something we've talked about at the beginning of the class. So her doctor is going to come get her, but she doesn't want to be disruptive to the class. We're adults enough. Yes. You're going to be okay, Tonya, until your doctor gets here? Oh, your daughter. Your daughter. Okay. All right. And let me know if you need anything. I'm assuming you know what to do with this. Yes. You're fine. On your side. Got it. Got it. She's good. She's on her side. We're doing okay. All right. I'm glad that she is aware of herself enough to recognize when she's going to have this. We've talked about since the beginning of the class, so we've been notified that this was going to be an issue before. So we are going to go on. We're going to try to be mindful. I'm watching her, so you guys don't worry. With our other antibiotics, we did DNA and RNA, the ones that inhibit protein synthesis. These usually inhibit the ribosome. We're just recovering for now. All right. All right, ribosome inhibitors, these come in 2 major groups. These are going to be our aminoglycosides and our macrolides. Well, I guess it's 3 major groups, sorry. And we have our cyclins. Cyclins will include tetracycline, doxycycline, or glycylcycline. Okay. Within our aminoglycosides and our macrolides, we have a lot of mycins. Now, obviously, we've seen a couple of mycins already. We saw vancomycin and daptomycin. So you're going to have to remember whatever works for you, that those ones are going to be separate from the others. Okay. So with our other mycins, some obvious examples will be neomycin, like we see in Neosporin, streptomycin, or erythromycin. Those are some examples of those. Okay. Water or anything? You're fine. Rest, you're good to rest. No pressure. Absolutely. Got that good? Little tree, you got your jacket. Yeah, you have, no, you're fine. You got it? All right, so there's those drugs. So these are all antibiotics. We also have antifungals. We also the other ones. So I'm going to give a little mini list of the other ones that we need to know. What color have I not done? Red. For the antifungals, we have the azoles and amphotericin B. It's just on its own, okay? Usually if we're reaching for amphotericin B, the azole didn't work. So we usually reach for fluconazole, miconazole, or ketoconazole. Azole. We actually know of one azole that we've talked about previously that I hate to bring it up that fell into the folic acid category, and that was the sulfamethoxazole. But it's got sulfa and meth. I want you to focus on that, okay? All right. So the azole of that one doesn't count as much. There's one other azole that is a deviant, and it falls into the protozoa. For the protozoa, we have metronidazole and the quinines. Quinines are used for malaria. Many of them have end in quin. So chloroquine, primaquine, those guys are the quinines. They are specifically for malaria, which is a type of protozoa. For metronidazole, it's unique. We often use it for amoebas, which are a type of protozoa, but we also use it for bacterial infections or even some kinds of fungal infections. So it's a lot broader. We notice that it has azole at the end. It's the azole that went to the big metro. This is literally how I remember it. I know it sounds stupid, but this is how I remember it. So our other azoles are pretty defined. They're in a small spot. But this azole went to the big metro, and it treats a lot of different things, not just protozoa, but pretty much a lot of things. It works generally in anaerobic environments. Anywhere there's not oxygen, for pretty much any type of infection where there's not oxygen. Okay. All right, so that's our antifungals and our antiprotozoals. I'm going to switch to orange really quick so we can see it a little bit better. Our antihelminthics, we treat them with pyrantel, praziquantel, or ivermectin. You pretty much just need to know that these are antihelminthics. I'm not going to ask you how they're going to work, okay? But if I have a question up there that says which of these are antihelminthic drugs, and I have on there ivermectin, metronidazole, vancomycin, or tetracycline, then you should be able to pick it out as an antihelminthic. Make sense? Okay. And then our last one are our antivirals. These are going to be anti-HIV drugs. And all of these are either going to target reverse transcriptase, protease, or integrase. All of these are unique to HIV. So the drugs target those things. And there's a lot of different names for those types of drugs that I won't test you on the names of the drugs, but you do need to know that they target these parts of HIV. Most commonly, reverse transcriptase. Then we also have drugs that target flu. The most commonly one that I'm going to bring up on the test is an obvious one, Tamiflu. We can recognize that one, right? And then another one is acyclovir. Another version of this is called valcyclovir. Trade name for valcyclovir, Valtrex. Acyclovir and its derivatives are most commonly used to treat herpes or other DNA viruses. It can be a little bit more broadly used than just herpes viruses, okay? And that pretty much covers most of our drugs for the chapter. Like I said, flashcard chapter if ever there was one, okay? The chapter also talks about Kirby-Bauer assay and stuff like that. We've taught it before. It should be a reprise for you guys, a review for you guys, so I'm not going to cover that. We're probably not going to finish the Kahoot for this one. Are there any questions about any of the drugs up front? Okay. I know it's at 6:37, so we're technically done with the class. The activity that I had for this one talks about antibiotic resistance in, let's say, trying to exit the screen, but it's not letting me. There it goes. In gonorrhea, which we have talked about previously, is a huge, huge issue right now. Gonorrhea infections are more commonly resistant to antibiotics. Azithromycin used to be a common treatment for it. And what aspect of bacteria does azithromycin target? It targets the protein synthesis pathway. It's one of the mycins. Okay. Then we have looking at new antibiotics. Why do we want to test them for safety? Because obviously not all antibiotics are completely safe for us. We might have toxic byproducts that can affect the kidney or the liver and stuff like that, and might severely impact our microbial antagonism of our natural biome as well. What are consequences for communities if effective treatments are unavailable? Obviously, the spread of gonorrhea. People don't listen to other methods, which is the next one of the next topics, the bottom one, the fifth one. What are other methods that we could use to prevent the spread of STIs, barrier methods, and just education about having your partners get tested as well. But people are very resistant to having to do work to get their pleasure. So they typically aren't going to be listening to us about that. So we'll likely see an increased spread of gonorrhea and other antibiotic resistant STIs as time goes on. How does this reflect broader challenges in treating bacterial infections overall? As bacteria become increasingly resistant and they can spread on those genes for resistance to other bacteria, we're going to see more and more infections that might be untreatable, which is what we're facing now with some strains of gonorrhea that we're seeing. Okay, any questions about any of that? All right, so if you guys want to pack up and head up to the lab is unlocked, so you are welcome to head up here. I'm going to hang out here with Tanya until we're sure that her doctor's going to be able to come get her, okay? The lab is unlocked, so you're welcome to go hang out.